Every star you have ever seen is dying. Not in the way that word usually feels, not suddenly, not dramatically, not in any way you would notice from where you are sitting right now, but dying nonetheless, burning through the fuel that makes them shine, moving each one of them, every single point of light in the sky above you, toward a moment when the burning stops, when the light goes out, when what was a star becomes something else, something dark and cold and quiet. The sun that rose today has been dying for 4.6 billion years. It has been burning hydrogen into helium at a rate of 600 million tons per second for nearly 5 billion years, and it will continue doing so for roughly 5 billion more. And when that fuel is finally exhausted, when the core runs out and the outward pressure of fusion can no longer hold the star up against its own gravity, the sun will change. It will swell. It will redden. It will eventually shed its outer layers into space and leave behind a small, dense, cooling remnant. A white dwarf, Earth-sized, fading slowly over billions of years into the dark. No explosion, no final flash, just a slow, patient dimming. That is the sun's future, and it is not unique. Every star in the sky above you tonight is on the same trajectory. Some have millions of years left. Some have billions. A few, the smallest, dimmest, most patient stars in the universe, have trillions. But all of them are moving in the same direction. All of them burning through something finite. All of them heading, with the absolute certainty of physics, toward darkness. And the universe, the whole of it, the 2 trillion galaxies and the hundreds of sextillions of stars and the vast dark spaces between them, is heading somewhere too. It is heading toward a state that physicists have a name for: heat death, a condition of maximum entropy where every energy gradient has been exhausted, where no process can occur, where the temperature everywhere is the same, indistinguishably close to absolute zero, and nothing can ever happen again. Not a dramatic end, not a collapse or an explosion, just a slow, patient arrival at a state of permanent stillness. A universe that has used up everything it had, and now simply is, forever. This is not speculation. This is not philosophy. This is what the equations say. The laws of thermodynamics, confirmed by every experiment ever conducted, point to a universe moving toward higher and higher entropy, toward more and more disorder, more and more uniformity, more and more sameness, and a universe at maximum entropy is a universe where nothing can change. Nothing. And it will remain that way for a duration that no number can capture. That is where we are going. But here is the thing worth holding on to before we follow the universe all the way to its end. The thing that makes this more than just an exercise in cosmic melancholy. We are here right now, in this specific moment in cosmic time, 13.8 billion years after the beginning, a third of the way through the era when stars still burn, we exist. We are alive, in the middle of the universe's one brief window of light. And that window is open right now. Tonight, while you are listening to this, the stars are burning outside, in every direction, in numbers beyond any count. The universe is not dark, not yet, not for an enormous span of time still to come, but it already started. The death of the universe began in the first second after the Big Bang. Every second that has passed since then has been a second of a story moving toward its ending. And the story is extraordinary. Let us tell it from the beginning, not the beginning of everything, but the beginning of now. The universe as it is tonight. Because before you can understand where it is going, you have to understand where it stands. Step outside tonight if you can imagine it. Stand somewhere away from city lights. Somewhere the sky is dark enough to show you what is actually there. Look up, let your eyes adjust, and slowly, over the course of minutes, the sky will fill. What you are seeing when you look at the night sky with your naked eye is several thousand individual stars, all of them in the Milky Way, all of them within a few thousand light years of Earth, all of them within a vanishingly small neighborhood of the galaxy we inhabit. The most distant star visible to the naked eye under perfect conditions is a blue hypergiant called Eta Carinae, roughly 7,500 light-years away, a star so massive and so luminous that it emits nearly 5 million times the energy of the sun. It is enormous even by stellar standards, and it is going to explode, probably within the next 100,000 years, in one of the most violent events the local universe will have seen in recent cosmic history. But it is still just one star, one of several thousand you can see, one of 2 to 400 billion in the Milky Way alone. And the Milky Way is one of roughly 2 trillion galaxies in the observable universe. 2 trillion. Each galaxy contains, on average, hundreds of billions of stars. Some contain fewer. The smallest dwarf galaxies, irregular, loosely structured, dimly lit, may contain only a few hundred million. The largest, the great elliptical giants at the centers of rich galaxy clusters, may contain several trillion. And somewhere in the middle, a fairly ordinary spiral galaxy in an unremarkable corner of a modest galaxy cluster, our Milky Way holds somewhere between 200 billion and 400 billion stars. The total number of stars currently burning in the observable universe is approximately 200 sextillion. That is a 2 followed by 23 zeros. If you could somehow count them at a rate of 1 per second, never sleeping, never pausing, it would take you more than 6 quadrillion years to finish. 40 times longer than the current age of the universe. And yet, despite this abundance, despite the almost unimaginable wealth of light and fire and nuclear energy burning across 2 trillion galaxies, the universe is in decline. It has been in decline for 10 billion years. The universe reached its peak of star formation during what cosmologists call cosmic noon, a period roughly 3 to 4 billion years after the Big Bang, when conditions in the universe were most favorable for stellar birth. Galaxies were younger then, denser, richer in gas, the raw material of star formation. Gas clouds were collapsing into new stars at a rate perhaps 10 times higher than they are today. The universe was actively, energetically, almost furiously building itself. That moment peaked, and it has been slowly declining ever since. We are now at 13.8 billion years, living through the long afternoon of the universe's most productive period. New stars are still forming. The Milky Way produces perhaps 2 or 3 new stars per year, and star-forming regions across the cosmos are still active, but the overall rate is a fraction of what it once was. The universe is building more slowly, burning more quietly. The intensity of cosmic noon is gone, replaced by something that is still beautiful, still active, but measurably and inexorably winding down. The universe tonight is spending, not earning. To understand the shape of what it contains and what it will lose, it helps to think about the universe's matter budget. The ordinary matter you can see, the stars, the gas, the dust, the planets, everything that interacts with light, accounts for only about 5% of the universe's total energy content. 5%. The rest is invisible. Dark matter, which interacts gravitationally and gives the cosmic web its structure but emits no light, accounts for roughly 27%. And the remaining 68% is something we call dark energy, a property of space itself that produces a repulsive effect, pushing the universe apart, accelerating the expansion that has been going on since the beginning. Dark energy is not well understood. We know it exists because the universe's expansion is speeding up, and something must be responsible for that. We know its rough magnitude because we can measure the acceleration. But we do not know what it is at a fundamental level. We have given it a name, and the name is a placeholder for a mystery. What we do know is what dark energy does. It expands space. And as space expands, galaxies that are not gravitationally bound to each other, not held together by their own mutual gravity, drift apart. The expansion carries them away from each other, and the acceleration means they are drifting apart faster and faster over time. This has a consequence that is easy to miss but important. As galaxies move apart, the light they emit has to travel a greater and greater distance to reach us. At some point, for galaxies that are already very distant, the space between them and us is expanding faster than light can cross it. Those galaxies are already beyond our reach. Their light will never arrive. They have crossed what physicists call the cosmic event horizon, the boundary beyond which no signal from them can ever reach us, not because anything is stopping it, but because space is growing faster than it can travel. Right now, the observable universe, the region from which light can still reach us, is roughly 93 billion light years in diameter. But over time, as the expansion accelerates, more and more galaxies will cross the horizon and disappear from our observable universe forever. The local group, the collection of galaxies that includes the Milky Way, Andromeda, and about 50 smaller companions, all bound together by their mutual gravity into a structure roughly 10 million light years across, will stay together. Gravity within the local group is strong enough to resist the expansion. But everything beyond the local group will eventually be lost. Galaxy by galaxy, cluster by cluster, the universe beyond our gravitational neighborhood will recede past the horizon and disappear. In a few 100 billion years, a civilization in whatever the Milky Way has become will look out at the universe and see almost nothing. Not because the universe is empty, but because everything beyond the local group will have receded beyond the reach of light. They will be cosmologically alone in a way we are not. We can look out right now and see 2 trillion galaxies. That ability, that view, is temporary. We happen to exist in a cosmological era where the universe is still observable in all its richness. Future observers, if any exist, will have much less. Most of what we can see tonight will eventually be lost to the horizon. And what remains, the local group, will have its own transformation to undergo. A slow, inexorable transformation that begins not in the far future but in the relatively near one. A star is a balancing act. On one side is gravity, the force that pulled a cloud of gas together in the first place. Hydrogen mostly, drifting in the space between other stars, gradually accumulating. Over millions of years, the cloud contracts. Gravity has no agenda, simply pulls inward always. The cloud grows denser at its center. The temperature rises. The pressure builds. The atoms in the core are squeezed closer and closer together until they are moving so fast, heated by the compression to temperatures of tens of millions of degrees, that something remarkable becomes possible. At those temperatures, hydrogen nuclei, single protons, moving at fractions of the speed of light, begin to collide with enough force to overcome the electromagnetic repulsion between them. They fuse. 2 protons become a deuterium nucleus. Then another proton joins. Then another. After a series of steps, a chain of reactions that the physics of the early universe made inevitable, 4 hydrogen nuclei have combined into 1 helium nucleus. And in the process, roughly 0.7% of the mass of those 4 protons has been converted directly into energy. Not stored, not transferred, converted. Mass becoming energy. The most direct expression of Einstein's equation that the universe regularly performs. That energy, carried by photons and neutrinos, pushes outward from the core. It pushes against the weight of all the gas above it. And for a long time, the inward pull of gravity and the outward push of fusion energy reach equilibrium. The star settles, it stabilizes, it burns. This is a star, a self-regulating nuclear furnace, sustained by the balance between 2 forces, powered by the conversion of hydrogen into helium. As long as there is hydrogen to burn, the star shines. And here is the first thing to hold onto. The size of a star determines almost everything about its life. Its temperature, its color, its luminosity, the length of its life, the manner of its death. And the relationship between mass and lifespan is backwards from what you might expect. Massive stars burn faster, much faster. A star 10 times the mass of the sun contains 10 times more fuel, but it burns that fuel at a rate thousands of times higher. The increased gravity in a massive star compresses the core to higher temperatures, which drives faster and more energetic fusion reactions, which produce more light and heat. A star 10 times the sun's mass is not 10 times brighter than the sun. It is 10,000 times brighter. That extraordinary luminosity burns through its fuel in a fraction of the time. The most massive stars in the universe, the blue supergiants, the hypergiants, the monsters at the top of the stellar mass distribution, live for perhaps 1 to 10 million years. A few million years of furious burning, and then a catastrophic end. Core collapse, a supernova, an explosion that in its peak luminosity can briefly outshine the entire galaxy that contains it. Billions of stars, outshone by one dying one. Stars like the Sun, middle weight, middle temperature, middle everything, live for about 10 billion years. Patient, steady, not dramatic in their life or their death. They swell into red giants near the end, shed their outer layers, and leave white dwarfs. No explosion, just a long, slow conclusion. And then there are the red dwarfs. Red dwarfs are the stars that almost nobody talks about when they talk about the night sky. They are not visible to the naked eye. They are not the subjects of mythology or constellation maps. They have no famous representatives in the cultural vocabulary of stars. They are dim, cool, red, small, typically between 8 and 50% of the sun's mass, and extraordinarily common. 3 out of every 4 stars in the Milky Way is a red dwarf. Proxima Centauri, the nearest star to our solar system, just 4.24 light-years away, our nearest cosmic neighbor, is a red dwarf. It emits about 0.17% of the sun's luminosity. If you replaced the sun with Proxima Centauri, the sky at noon would be darker than a cloudy day. The star would appear as a dim reddish point, not a disk. The surface of the Earth would freeze, but Proxima Centauri will still be burning, still fusing hydrogen into helium, when the universe is 500 times older than it is now. It has a lifespan of approximately 4 trillion years. It is about 5 billion years old today. That means Proxima Centauri, the star closest to us, the one we have studied most carefully, the one we have mapped for nearby planets, has used roughly 1/8 of 1% of its total lifespan. It is, by stellar standards, a newborn. Red dwarfs achieve this longevity through a structural advantage that larger stars lack. In a star like the Sun, the core is separate from the outer layers. Fusion happens in the core using the hydrogen present there. The outer layers, which contain the majority of the star's hydrogen, do not mix into the core. The Sun will eventually exhaust the hydrogen in its core and die, even though enormous quantities of unburned hydrogen remain in its outer envelope. Cannot access that hydrogen. It will die with most of its fuel unspent. Red dwarfs are fully convective. The entire star circulates like a slow-moving lava lamp, but made of plasma at millions of degrees. Hydrogen from the outer layers continuously cycles down into the core. Helium produced by fusion in the core cycles outward. The red dwarf uses its entire hydrogen supply, not just the fraction in its core. And because it burns its fuel at such a low rate, because the fusion reactions in its small, lower temperature core proceed so slowly, that entire supply lasts for an almost incomprehensible length of time. A red dwarf with 1/10 the mass of the Sun, burning its entire hydrogen supply at its leisurely rate, will shine for approximately 10 trillion years. 10 trillion years. The universe is 13.8 billion years old. 10 trillion years is roughly 725 times that. And these stars, these dim, unassuming, almost invisible stars that fill the galaxy and fill the universe, are the last light the cosmos will ever produce. When they finally go dark, the universe's age of stars will be over. Forever, in approximately 4.5 billion years, the night sky will change. The change will be slow at first, so slow that no individual generation of any species alive at the time would notice it from year to year. But over thousands of generations, over millions of years, the constellation patterns will distort. The positions of the nearest stars will drift against the background of more distant ones, and then something larger will begin to happen. A smear of light will appear. At first, it will be faint, a slight brightening in one region of the sky, a new glow that doesn't match any familiar structure. But over time, over millions of years of looking, the glow will grow. It will resolve, and eventually it will become unmistakable. The Andromeda Galaxy is coming. Right now, Andromeda, the nearest large galaxy to the Milky Way, a spiral galaxy roughly 2.5 million light-years away, containing perhaps 1 trillion stars, is approaching us at approximately 110 kilometers per second. Drawn by our mutual gravity across 2.5 million light-years of space, The two largest members of the local group have been falling toward each other since long before the sun was born. In about 4.5 billion years, they will reach each other. The collision, though that word is somewhat misleading, will be unlike anything in human experience. When two galaxies merge, the stars within them rarely collide directly. The average distance between stars in either galaxy is several light years. When the galaxies interpenetrate, passing through each other, the probability of any two individual stars occupying the same space is extraordinarily low. What happens is not a crash but an interaction, a gravitational dance. The two galaxies will pass through each other over the course of hundreds of millions of years. Gravitational tides, the differential pull of one galaxy's mass on different parts of the other, will stretch both structures into long tidal tails. Streamers of stars pulled outward by the encounter, arcing away from the main bodies of both galaxies in enormous curved arcs hundreds of thousands of light years long. Then, slowed by the energy lost to those tidal disruptions, the galaxies will fall back together. They will pass through each other again and again, each pass more distorted, more mixed, more chaotic than the last. Over perhaps 2 billion years, a long, slow process of collision, rebound, and remerger, the two spiral galaxies will be thoroughly mixed. What emerges from this process will not be a spiral. The ordered disk structure of the Milky Way, the beautiful pinwheel shape we see in images of other spiral galaxies, the organized rotation that produces the spiral arms, requires ongoing star formation to maintain its appearance. Young, hot, blue stars in the arms trace the density waves that produce the spiral pattern. As the merger disrupts the ordered rotation and triggers new bursts of star formation followed by their exhaustion, the disk structure dissolves. The product of the Milky Way and Andromeda merger will be an elliptical galaxy, round, diffuse, filled with stars in random orbits rather than organized rotation. Redder and quieter than either parent, the kind of galaxy that looks in astronomical surveys old, settled, done with the vigorous star formation of its youth. Astronomers have already given this future galaxy a name, Milkomeda. Our sun, if it is still burning at the time of the merger, and the timing is close enough that it should be, will almost certainly be in a very different location within the merged galaxy than it occupies now. The gravitational disruption of the merger will scatter stars from their current positions across the new merged structure. The sun might end up in the outer halo, far from where any galactic center was, or it might end up much closer to the merged core. The details depend on the specific dynamics of the encounter in ways that no simulation can predict with certainty. What can be said with confidence? The sky as seen from Earth during and after the merger will be unrecognizable. During the first close passage of the galaxies, the night sky will be spectacular in a way no human has ever seen. Millions of new stars, ignited in the bursts of star formation triggered by the compression of gas clouds during the encounter, will fill regions of the sky that were previously sparse. The Milky Way's familiar band, the edge-on view of our galactic disk, will be replaced by something more chaotic, more luminous in places, darker in others, and crossed by the structure of the incoming Andromeda galaxy. It will be the most visually extraordinary sky any observer on Earth will ever have witnessed. If there is anyone to witness it, the sun, remember, is also aging. In about 1 to 2 billion years, long before the Andromeda collision, the sun's increasing luminosity will warm the Earth beyond the point where liquid water can persist on its surface. The oceans will evaporate. The atmosphere will change. Whatever life exists on Earth at that time will need to have moved elsewhere, evolved to tolerate radically different conditions, or ended. The Earth as a habitable world has roughly 1 billion years remaining. The Andromeda collision happens after that. It happens in a cosmos where Earth is already a hot, waterless rock, the sun already brighter and hotter than it is today, the solar system already transformed by the early stages of the sun's evolution toward its red giant phase. The universe doesn't wait for life to be ready for the next thing. It simply moves. In approximately 5 billion years, the sun will run out of hydrogen in its core. Not in its outer layers, not in its entirety, Just in the central region where fusion has been happening, the innermost 20% or so of the sun's mass, which is where the temperatures are high enough to sustain the proton-proton chain. The rest of the sun will still contain vast amounts of hydrogen, but the core will be exhausted, filled now with helium, the ash of 50 billion years of fusion, inert, unable to sustain further burning. Without the outward pressure of fusion to hold the core up, it will begin to contract under its own weight. The contraction will be slow at first, a gradual inward settling of the helium core under gravity, releasing gravitational energy as heat. That heat will spread outward into the surrounding hydrogen, the hydrogen that hasn't fused yet, sitting in a shell around the exhausted core. And that heat will be enough eventually to ignite fusion in the shell. Shell burning, hydrogen fusing not in the core but in a layer surrounding it. And the energy released by that shell burning will do something unexpected to the outer layers of the sun. It will push them outward, not gently, not gradually on the same timescale as the core's 5 billion year burn. Much faster, over millions of years fast by stellar standards, the sun's outer envelope will expand. It will swell. The surface will cool as it stretches across a larger area, and as it cools, it will redden. The sun, seen from a great distance, will become what astronomers call a red giant, a star with a radius perhaps 100 to 200 times larger than it is today. Its surface temperature dropped from about 5,800 Kelvin now to perhaps 3,000 to 4,000 Kelvin. A red giant sun, filling a much larger portion of Earth's sky. Assuming Earth is still there, Mercury will be consumed, its orbit engulfed by the expanding outer atmosphere of the sun. Venus, too. Earth's fate depends on the specific rate at which the sun loses mass during its expansion, which determines how much Earth's orbit widens. Some models suggest Earth just barely avoids being swallowed. Others suggest it is engulfed. Either way, the surface will have been scorched to temperatures that vaporize rock. The Earth as anything recognizable will be gone long before this, long before the red giant phase. The increasing luminosity of the sun's normal life will have already sterilized the surface. But the sun as a red giant will be something worth imagining, regardless. A sphere of gas 100 times the size of the current sun, glowing red-orange, extending outward into space, enormous and cool and diffuse. Not a compact, brilliant, blinding disk, but something vast and spreading. A giant, as the name suggests. In this phase, the sun will burn for perhaps 1 billion years or so, though not steadily. The red giant phase includes episodes of thermal pulsing, where the fusion in the shell becomes unstable, flares up, pushes the outer layers outward, then settles again. Each pulse is a slow wave of expansion and contraction. Slow by human standards, not by stellar ones. Eventually, the core, compressed by gravity through all of this, will reach temperatures high enough to ignite the helium that has been accumulating there. Helium fusion is more demanding than hydrogen fusion. It requires temperatures of around 100 million Kelvin instead of 10 million, and it runs on a different reaction, 3 helium nuclei fusing into 1 carbon nucleus, the triple alpha process. When helium ignites in the core of a red giant, it does so with what astronomers call the helium flash, a runaway burst of fusion in the degenerate core that releases, in a matter of hours, as much energy as the sun normally produces in 100 million years. The energy doesn't reach the surface. It's absorbed by the star's interior, but the core is fundamentally restructured. A new phase of burning begins. The star shrinks somewhat from its red giant dimensions, brightens slightly, and burns helium for perhaps 100 million years. Then the helium in the core runs out too. What follows is a complex, unstable period of dual shell burning. Helium burning in one shell, hydrogen burning in another shell outside it, that drives increasingly large thermal pulses. Each pulse ejects a shell of material from the sun's outer layers. These shells, illuminated by the ultraviolet radiation from the increasingly exposed hot core, glow in characteristic colors: green, blue, red, depending on their composition. From a distance, this structure is one of the most beautiful things in the observable universe. Planetary nebula. the sun will produce one, a shell or series of shells of ejected gas, expanding outward at perhaps 10 to 20 kilometers per second, glowing for tens of thousands of years before dissipating into the interstellar medium. And at the center of the planetary nebula, exposed now, no longer surrounded by the outer layers that have been shed, the core, a white dwarf. What is left of the sun will be a white dwarf roughly the size of Earth, composed primarily of carbon and oxygen. The compressed, hot remnant of a core that spent billions of years fusing hydrogen and then helium, now unable to fuse anything further. The temperature at the surface of a newly formed white dwarf can be 100,000 Kelvin, far hotter than the sun is today. But without any energy source beyond its own residual heat, it will simply cool, slowly, radiating away its heat into the surrounding space over billions of years. The sun's white dwarf remnant will cool for a very long time. It is still cooling in a very real sense in the universe's far future. But it will never completely stop, not in any timescale that the universe will experience before heat death changes the conditions. One star's story. Multiply it by the hundreds of billions of stars in the Milky Way, by the hundreds of sextillions of stars in the observable universe, and the scale of what is happening becomes clearer. The universe is slowly filling up with the remnants of dead stars. And what it is running out of is the stars themselves. Imagine a photograph of the universe taken every billion years, placed in sequence. If you could watch those photographs, billions of years compressed into something viewable, you would see the universe age before you. And the aging is visible, not metaphorical, actually visible in the light itself. The young universe glows blue-white. The spiral galaxies are filled with young, massive, hot stars, blue supergiants, O-type and B-type stars that burn with extraordinary intensity. These stars don't live long enough to be patient, so the galaxies that contain them are constantly producing new ones to replace the ones that die. The star formation rate is high. The light is bright and blue and fierce, but over billions of years, the blue begins to fade. The massive stars die. They run through their fuel in millions of years and explode, leaving behind neutron stars and black holes. The gas that might form new massive stars is depleted, or has been heated by the explosions of old ones, or has been expelled from the galaxy altogether by the energy of active galactic nuclei, the supermassive black holes at galaxy centers that occasionally feed and, in feeding, release enormous jets of energy that push gas outward and suppress star formation. What is left burns redder. The mid-weight stars, stars like the sun, continue burning. Their lifetimes of 10 billion years mean they are still present long after the blue giants are gone. But they are cooler. Their light is yellow-white, not the intense blue-white of the massive stars. The galaxy's color shifts. Its overall luminosity drops. Not all at once, never all at once, but steadily over billions of years. By the time the universe is 50 billion years old, roughly 3.5 times its current age, the character of a typical galaxy will be very different from today. Star formation will have slowed dramatically. The interstellar medium, the gas and dust that is the raw material for new stars, will have been depleted by billions of years of star formation and recycled by stellar winds and supernovae, but not replenished as quickly as it is used. The remaining gas will be more diffuse, more spread out, less concentrated into the dense clouds where star formation happens. New stars will still be forming, but slowly, mostly smaller stars, red dwarfs again, the small ones that dominate by number and will dominate increasingly as the population of larger stars is exhausted. The galaxy will be a quieter place, redder, dimmer, older looking, and beyond any individual galaxy, the universe at 50 or 100 billion years will be visually impoverished compared to today. The great galaxy clusters that fill our current maps of the large-scale structure, the clusters connected by filaments of dark matter, forming the cosmic web, will still be there. But the galaxies within them will have merged, many of them, into large elliptical systems. The spiral structure so common today will be increasingly rare. The ellipticals, rounder, redder, quieter, will dominate. The cosmic web itself, on the largest scales, will persist. Dark matter doesn't dissipate. The filaments will still be there, but the glowing, luminous matter tracing those filaments will be dimmer and dimmer as the stellar population ages. It is worth pausing on the galaxy clusters and what happens to them over this timescale. Within a rich cluster, a gravitationally bound collection of hundreds or thousands of galaxies, the galaxies interact. They collide and merge. The small galaxies are tidally stripped by the larger ones. Material falls into the center of the cluster's gravitational potential well. Over billions of years, a typical rich cluster evolves toward a configuration dominated by a single enormous elliptical galaxy at its center, the product of billions of years of mergers, surrounded by the stripped and dissolved remnants of the smaller galaxies that were consumed along the way. These central dominant galaxies, called CD galaxies today, though they will be far more extreme versions of their current selves in the far future, will be extraordinary objects. Trillions of stars in a single galaxy, but older stars, redder stars, stars that are themselves aging, their fuel supplies diminishing, the brightest of them dying first and leaving the redder, dimmer, longer-lived ones behind. The universe at 100 billion years is still lit, still burning, still active, but it is burning with the light of an afternoon that knows it is heading toward evening. The blue is gone, the white is dimming, what remains is red, and the red will dim next. It will just take much, much longer than everything that came before. After the sun dies, after every star like the sun has died, the universe enters a new phase. Not a dramatic one, not a phase marked by a specific event, just a slow, gradual transition into an era that has no precedent in any cosmological epoch a human civilization has ever existed in. The age of red dwarfs. The last large stars will have died of old age somewhere around 15 to 20 billion years from now. Their remnants, white dwarfs, neutron stars, will still be there, cooling. The supermassive black holes at galaxy centers will still be there, mostly dormant, occasionally feeding when something wanders close enough. And then there will be the red dwarfs, hundreds of billions of them in the Milky Way's remnant, trillions across the local group. The universe's last burning stars, still fusing hydrogen into helium, still shining, dimly, redly, patiently, into a universe that has grown very quiet around them. Imagine that universe. Imagine being somewhere in Milkomeda, whatever the merged Milky Way and Andromeda galaxies have become 100 billion years from now. The galaxy around you is a large elliptical. The organized spiral structure is gone. The stars occupy random orbits rather than the ordered rotation of a disk. There are no spiral arms, no bar, no obvious center of star formation activity. The night sky from any hypothetical planet in that galaxy would be extraordinary and alien. The red dwarfs glow their dim, reddish light. Many of them, most of them, would be orbited by planets. Red dwarfs are now known to commonly host planetary systems, and many of their planets, particularly in the habitable zones close to the star, could theoretically maintain liquid water on their surfaces. The habitable zone of a red dwarf is much closer to the star than the habitable zone of the sun. Because the star is so much dimmer, a planet needs to be much closer to receive enough warmth. But closer means tidal locking becomes likely. The planet rotates at the same rate as it orbits, always showing the same face to the star, the way the moon always shows the same face to Earth. One side in permanent day, one side in permanent night. Whether life can thrive under those conditions is an open question, one of the most important open questions in astrobiology. Some models suggest the atmospheric circulation on a tidally locked planet could distribute heat effectively enough to maintain habitable conditions on a wide band around the terminator, the line between day and night side. Others suggest the conditions are too extreme. But in the age of red dwarfs, if life or its successors exist anywhere in the universe, it is almost certainly around red dwarfs. They are the only game left. The universe at 1 trillion years, 100 times the current age, but still well within the age of red dwarfs, would be dominated by these small, patient stars. No blue supergiants, no yellow dwarfs, no sun-like stars, just the red dwarfs, burning slowly, and the cold, dark remnants of everything else. and even the red dwarfs are aging. Here is something counterintuitive that happens as red dwarfs get old. As they consume their hydrogen supply and the composition of their stellar interior changes, they actually become slightly bluer and brighter for a time. The helium produced by fusion gradually increases the mean molecular weight of the stellar material, which slightly increases the core temperature, which slightly increases the fusion rate, which slightly increases the luminosity. An aging red dwarf glows a bit more intensely for a period, a cosmological swan song, a brief brightening before the final decline. But the hydrogen still runs out. And when it does, when the last of the fuel in a given red dwarf has been fused, there is no swell into a red giant. Red dwarfs are too small for that. Their cores, even fully compressed by gravity, cannot reach the 100 million Kelvin needed to ignite helium fusion. The helium they have produced simply sits in the core inert. The hydrogen burning stops. Gravity wins. The star contracts. Slowly, over millions of years, it shrinks. The gravitational energy of contraction heats the surface. Paradoxically, the dying red dwarf gets bluer and hotter looking for a time as it contracts, before the inevitable cooling dominates. Then it becomes a white dwarf. A small one by white dwarf standards, mostly helium and hydrogen, not the carbon-oxygen white dwarfs that sun-like stars leave behind. Dense, hot, and cooling, and then cooling further, and then cooling further still. One by one, over hundreds of billions of years, the red dwarfs reach the end of their fuel supplies. The universe's fires go out one at a time, not simultaneously, not even roughly simultaneously, each one at its own appointed time, determined by its mass and the precise history of its hydrogen burning. The larger red dwarfs first, then the mid-sized ones, then the smallest. The very smallest red dwarfs, those hovering just above the minimum mass required to sustain hydrogen fusion at all, approximately 8% of the sun's mass, will burn for approximately 10 trillion years. 10 trillion years. 10 to the 13th power. In a universe that is currently 1.38 times 10 to the 10th power years old, these stars will still be burning when the universe is 1,000 times older than it is now. They are the last ones. Picture it. The universe is approximately 100 trillion years old. In the vast time that has passed since the moment we call the present, the cosmos has expanded to a scale that makes its current size seem almost intimate by comparison. The observable universe, the region from which light can reach us, has not grown, because the expansion of space has continued to push the horizon outward while simultaneously pushing the distant galaxies beyond it. The universe is simultaneously larger and, in terms of what is reachable or observable, emptier. The local group, Milkomeda and its companions, has long since become the entire observable universe from any point within it. Everything beyond is unreachable, has been unreachable for tens of billions of years. Not destroyed, not gone, just beyond the horizon, receding forever. Within the merged galaxy, the inventory of matter is largely complete. The stars that will ever form have mostly formed and died. The gas that will ever be converted into stars has been converted, or dispersed, or locked into stellar remnants where it cannot participate in future star formation. The galaxy is a collection of remnants, billions of white dwarfs at various stages of cooling neutron stars left over from the supernovae of billions of years past, the central supermassive black hole, now quiet, its gas supply long since exhausted, and the red dwarfs. The last red dwarfs, not very many of them, relative to the number that once existed. The ones that burned fastest, that were slightly more massive, slightly brighter, have already gone out. Their white dwarf remnants are cooling in the dark. What remains are the smallest ones, the dimmest ones, the most patient ones. They burn so slowly that each one is essentially identical to how it was billions of years ago. Red, dim, tiny by stellar standards, but burning, fusing hydrogen into helium at a rate so low that the energy output per unit volume is less than the metabolic heat generated by a human body. These stars are barely stars by the standards of the universe's youth. They are embers, patient, ancient, impossibly long-lived embers. And they are going out. One of them is the last. We cannot know from here which one it will be. We do not know the exact masses of the smallest red dwarfs in the universe, or the precise rate at which they will burn through their fuel, or the specific moment when the last one will exhaust its hydrogen and begin the slow contraction toward its white dwarf remnant. The physics gives us the timescale, approximately 100 trillion years, but not the specific star or the specific moment. But it will happen. At some point in the universe's 100 trillionth year, the last star that is actively fusing hydrogen will run out of fuel. The process will not be sudden. The red dwarf will have been showing signs of aging for billions of years. The slight brightening, the shift in color, the increasing helium content of its interior. As the hydrogen in its core and its convective interior approaches exhaustion, the fusion rate will drop. The energy output will decrease. The star will cool slightly. Its light will redden further. If it were possible to see it from the outside, it would appear to be dimming, its reddish glow deepening toward infrared. This dimming will take millions of years. During those millions of years, a span of time longer than any human civilization has ever existed, longer than the Earth has had complex land life, longer than the sun has been shining, the last star will be fading. Not dramatically, not in a way that would feel fast from any external vantage point. Just slowly, steadily dimming. The fusion in the core will slow further. The outward pressure holding the star up against gravity will weaken. The star will begin to contract, not dramatically, not in a runaway collapse, but in the gradual, almost imperceptible way of something that has used up all its energy and is settling, compressing, becoming denser. As it contracts, the gravitational energy released will heat the surface. The star will appear, paradoxically, to brighten slightly and shift toward blue-white. Not from fusion, but from the heat of compression. This phase may last millions of years. It is the star's last light. Not the light of burning, but the light of falling. And then the cooling begins. The last star will cool. Its surface temperature will drop. The light it emits will shift from visible to infrared to far infrared. There will be a moment, not a dramatic one, not one marked by any particular event, when the wavelength of the light from the last star shifts beyond the range that human eyes would have recognized as light. When the photons it emits are too long wave, too low energy, to constitute what we call visible radiation. The last light the universe produces from stellar fusion will be invisible. It will be infrared radiation, heat, from a cooling white dwarf remnant, slowly losing the last of the energy produced over trillions of years of hydrogen burning. And that radiation will continue for a very long time, growing ever fainter, ever longer in wavelength, as the white dwarf cools toward the temperature of the surrounding universe. But the star, the last fusion-burning star, the last object in the universe actively converting hydrogen into helium and releasing the energy of nuclear burning, will have gone dark somewhere around 100 trillion years. And in that moment, in that particular moment in cosmic history, which the universe will reach whether or not anything is there to witness it, something ends that can never begin again. The Stelliferous Era, the Age of Stars, the period of cosmic history that began roughly 1 million years after the Big Bang, when the first population 3 stars ignited in the darkness of the young universe, will come to its end. An era spanning 100 trillion years, a number so large that every human concept of time becomes useless in comparison, will conclude. No more stars will ever form. Not because the universe lacks matter, white dwarf remnants and black holes and the thin dispersed gases of the intergalactic medium still contain enormous quantities of matter, but because that matter is no longer in a form or a configuration that can produce new stellar nurseries. The conditions of the universe at 100 trillion years, expanded, cold, dispersed, do not permit the kind of gas cloud collapse that produces stars. The entropy of the universe is too high. The matter is too spread out. The stars that exist at the moment the last one dies are the last stars that will ever exist. There will never be another one. Sit with that for a moment, not as a fact to be processed and filed, but as something to actually hold in your mind. The universe spent 100 trillion years making stars, building them, burning them, ending them, recycling some of their material into new ones. A vast, ongoing process of creation and destruction that produced, as a byproduct, the heavy elements that make chemistry possible, the planets that make surfaces available, the energy gradients that make complexity achievable. All of that ends with one star going dark. And the darkness that follows is not temporary. There is a particular quality to a light going out in a dark room. You notice it more than you noticed the light when it was on. When light is simply there, constant, present, expected, you stop seeing it. It becomes background, assumed. The room is lit, and that is the condition of the room, and you move through it without registering the light itself. But when the light goes out, something in you notices immediately. The darkness is not just the absence of light. It is the presence of something new, something that was not there before, a condition that announces itself. The last star going dark is something like that, not because anyone is there to notice, but because the universe itself changes in that moment. Not in its physics, the laws of thermodynamics have been moving toward this moment since the beginning, and they continue after it. But in its character, in what it is. Before the last star dies, the universe is a place where fusion happens, where hydrogen becomes helium and mass becomes energy and light crosses empty space and lands on surfaces and makes things warm, where there are places hotter than other places, where there are gradients of energy and where those gradients make things possible. After the last star dies, the universe is no longer any of those things. It is a universe of remnants, of things that were made but are no longer being made, of cooling embers and spinning relics and vast dark spaces between them. A universe that still contains enormous amounts of matter, but matter that has been used, that has burned through whatever it had to burn, that now simply is, slowly losing the last of its heat to the surrounding cold. The universe will never be as bright as it was in the first trillion years. It will never be as bright as it was tonight, while you are listening to this. The stars burning right now, the 200 sextillion stars burning across 2 trillion galaxies, pouring light and heat and ultraviolet and X-rays and gravitational waves into the cosmos, represent the height of something. Not the peak, we are before the peak in some ways, after it in others, but something close to the height of what the universe can do. And you are here for it, right now, tonight, in the one cosmological era when stars exist. The era that ends at 100 trillion years and will never come again. But the universe after the last star goes dark, that universe, as cold and quiet and dark as it will be, is not finished. The end of the stars is not the end of the story. It is just the end of the part that is lit. A long breath, the tone holds. Block 10, the degenerate era. Quadrillions of years. We are now in territory that feels genuinely alien. The universe described here has no analog in anything human. Let that strangeness into the writing, but keep the voice calm. The narrator is still here, still beside you, still making sense of it. The universe after the last star is not empty. This matters. This is worth saying clearly before anything else. The death of the stars does not mean the death of matter. It does not mean the cosmos has ended. The universe at 100 trillion years still contains an enormous, almost incomprehensible amount of mass. What it lacks is not matter. What it lacks is energy sources capable of producing starlight. The matter remains, but what it does, what it looks like, what the universe is transformed beyond anything the current cosmos suggests. What fills the post-stellar universe? White dwarfs, many billions of them in Milkomeda alone. The cooling remnants of every star below about 8 solar masses that has ever lived and died. White dwarfs are extraordinarily dense, more than 1 million times denser than water. A teaspoon of white dwarf material brought to Earth would weigh roughly 5 tons. They are composed primarily of carbon and oxygen, the ash of stars that burned hydrogen and then helium, and they are supported against further gravitational collapse not by pressure from nuclear reactions but by a quantum mechanical effect called electron degeneracy pressure. The electrons in the compressed material, forbidden by the Pauli exclusion principle from occupying the same quantum state, exert a resistance to further compression that holds the white dwarf up. This resistance does not require energy. A white dwarf does not consume fuel to remain stable. It simply is stable, supported, cools very slowly. A white dwarf formed from a sun-like star emerges from the planetary nebula phase at perhaps 150,000 Kelvin, hotter than most stars. Over billions of years, it radiates that heat away. The cooling slows as the temperature drops. Cooler objects radiate less effectively. So a white dwarf that cools from 150,000 Kelvin to 30,000 Kelvin relatively quickly will then take billions more years to cool from 30,000 to 10,000 Kelvin, and even longer to cool from 10,000 to 5,000. The very oldest white dwarfs in the universe, those formed in the first billion years after the Big Bang, are still hot by the standards of a universe where the ambient temperature of space is 2.7 Kelvin. They are cold compared to stars, but not cold by absolute standards. Over quadrillions of years, over timescales 1,000 times longer than the entire stelliferous era, white dwarfs cool toward the temperature of the surrounding universe. When a white dwarf has cooled to the ambient cosmic temperature, it emits no more radiation than the space around it. It becomes, effectively, invisible, a dense cold sphere of compressed carbon and oxygen, dark, floating in a dark universe, no different energetically from the space that surrounds it. Physicists call this state a black dwarf. No black dwarfs exist yet. The universe is not old enough. The cooling time for even the oldest white dwarfs is longer than the current age of the universe. Every white dwarf in existence today is still hotter than it will eventually be. In the era we are now describing, the degenerate era, they are cooling. Slowly but inexorably, the white dwarfs are fading to black. The neutron stars are there too. Neutron stars are what certain massive stars leave behind after supernovae. The collapsed cores of stars that died violently, compressed not to white dwarf density but further, to the point where electrons and protons have merged into neutrons. A neutron star typically contains more mass than the sun packed into a sphere about 15 kilometers across. If the Earth were compressed to neutron star density, it would be roughly the size of a tennis court. Young neutron stars are often pulsars, rapidly spinning, emitting beams of radio waves from their magnetic poles. As a pulsar spins, those beams sweep past the Earth like a lighthouse beam sweeping past a ship, and we detect a regular pulse of radio emission, hence the name. The most rapidly spinning pulsars rotate hundreds of times per second, but pulsars spin down. The emission of electromagnetic radiation carries away angular momentum, slowing the pulsar's rotation. Over millions of years, a pulsar slows from hundreds of rotations per second to tens, then to 1 or 2, then below the threshold for pulsar emission. In the degenerate era, the neutron stars will have long since stopped pulsating. They will simply be there, dense, cold, dark, inert. And somewhere in the degenerate era, if a hypothesis that has not yet been confirmed experimentally is correct, the ordinary matter in white dwarfs and neutron stars may begin to dissolve. Proton decay. The proton, the positively charged particle at the center of every hydrogen atom, the building block of ordinary matter, is, in the standard model of particle physics, perfectly stable. It does not decay. It has been observed experimentally to be stable over timescales much longer than the current age of the universe, with no measured decay events. But the standard model is not a complete theory. Physicists are confident it is incomplete. It does not include gravity, does not explain dark matter or dark energy, does not tell us why there is more matter than antimatter in the universe. Various extensions of the standard model, theories that attempt to unify the fundamental forces, predict that the proton should eventually decay. Not quickly, but eventually. The predicted proton lifetime in different theoretical frameworks ranges from about 10 to the 33rd power years to 10 to the 40th power years or beyond. This is an enormous range, many orders of magnitude, because the details of the specific theory determine the rate. But the general prediction from a wide class of theoretical models is that protons are not eternal. If proton decay occurs at the faster end of predictions, around 10 to the 34th years, then the white dwarfs and neutron stars of the degenerate era will slowly dissolve. Not explosively, proton decay, when it occurs for an individual proton, releases a small amount of energy in the form of gamma rays and positrons. In a white dwarf containing roughly 10 to the 57th protons, individual proton decays will be occurring at a very low rate. The energy released will keep the white dwarf slightly warmer than it would otherwise be, a tiny faint glow from the slow disintegration of its own matter. But over 10 to the 35th or 36th years, essentially all the protons in a white dwarf would have decayed. The dense sphere of carbon and oxygen would dissolve into a diffuse cloud of light particles, gamma rays, neutrinos, positrons, and disperse into the surrounding space. The white dwarfs and neutron stars would be gone. What remains if proton decay occurs, what the universe contains after all ordinary matter has dissolved, is primarily the black holes. And the black holes, vast and dark and patient, will sit in the spaces where galaxies used to be for longer than everything that has come before. The black hole era is a phase of the universe that no human analogy can capture. Not because the concepts are too abstract. The concepts are simple enough. Black holes, existing in a dark and expanded universe, very slowly losing mass to Hawking radiation. Simple to state, almost impossible to feel in the gut the way the facts require. The black hole era spans from roughly 10 to the 40th power years to 10 to the 100th power years. 10 to the 100th power is called a googol, the number that gave the internet search company its name misspelled. A googol is a 1 followed by 100 zeros. The black hole era lasts from 10 to the 40th to 10 to the 100th. The duration of the black hole era is approximately 10 to the 100th years. Let us try to put this in context. The age of the universe right now is 1.38 times 10 to the 10th power years. The end of the stelliferous era, the death of the last star, is approximately 10 to the 14th years. The end of the degenerate era, the dissolution of the last white dwarfs, assuming proton decay, is approximately 10 to the 40th years. All of cosmic history from the Big Bang to the present moment is roughly 10 to the 10th years. All of cosmic history from the Big Bang to the death of the last star is roughly 10 to the 14th years. All of cosmic history from the Big Bang to the end of the degenerate era is roughly 10 to the 40th years. The black hole era begins at 10 to the 40th and ends at 10 to the 100th. Everything that has ever happened, from the Big Bang to the death of the last white dwarf, happens within the first 10 to the 40th years. The black hole era is 60 orders of magnitude longer than that entire preceding history. To say this another way, if you compress the entire history of the universe from the Big Bang to the death of the last white dwarf into a single second, the black hole era would last more than 10 to the 50 years in that compressed timescale. There is no number of human words that makes this comprehensible. The black hole era is simply, in an almost definitional sense, beyond imagination. And yet, it is a real phase of the universe. It will happen. The equations say so. In the black hole era, the universe is dark. It is not dimly lit. It does not have the faint glow of cooling white dwarfs or the infrared whisper of dying red dwarfs. The white dwarfs, if proton decay has dissolved them, are gone. The neutron stars are gone. The ordinary matter of the universe, the protons and neutrons that make up atoms, that make up you, that make up everything you have ever touched or seen, will have decayed into lighter particles and radiation, dispersed across a universe so expanded that the average density of anything is almost zero. What remains is the black holes, and the universe around them is very, very dark. The ambient temperature of the universe, the temperature of the cosmic microwave background, which is currently 2.7 Kelvin, has been dropping since the universe was young. As the universe expands, the photons of the CMB lose energy, their wavelength stretched by the expansion. Their temperature drops inversely with the scale factor of the universe. By the time of the black hole era, the temperature of the CMB will have dropped to something like 10 to the negative 30th power Kelvin, a number so close to absolute zero that the difference is meaningless in any practical sense. The universe is essentially at absolute zero. In this near absolute zero environment, the black holes sit. The supermassive black holes, the ones that occupied the centers of galaxies, built up over billions of years of accretion and mergers, are the largest. The supermassive black hole at the center of what used to be the Milky Way has a mass of roughly 4 million solar masses today. By the time of the black hole era, if it has fed on additional matter over the intervening trillions of years, it could be considerably more massive. And there are larger black holes in the universe. The supermassive black hole at the center of M87, a giant elliptical galaxy in the Virgo cluster, contains about 6.5 billion solar masses. These are the largest objects in the universe's far future. Not matter as we think of matter, not collections of atoms, but pure curvature of space-time, surrounded by event horizons beyond which nothing can escape. They will occasionally interact. Over the vast timescales of the black hole era, black holes will sometimes approach each other. Not often. The universe will be so expanded, the distance between black holes so enormous, that the probability of any two black holes encountering each other in any given year will be extraordinarily low. But 10 to the 40th years is an extraordinary span of time. Even improbable events, given enough time, occur. When two black holes approach each other closely enough, gravitational radiation, gravitational waves, ripples in space-time, carries energy away from the system, causing the black holes to spiral inward toward each other. Eventually, they merge into a single larger black hole, and the merger sends gravitational waves propagating outward across the empty universe. These ripples will cross a cosmos that has nothing else in it. No stars, no galaxies, no planets. Just the expanded space-time and the thin background of particles left over from all the processes that have ended. The gravitational wave from a black hole merger in the black hole era will be, in all likelihood, the last energetic event the universe produces for an extraordinarily long time. But even the black holes are dying. Slowly, almost imperceptibly slowly, but dying. In 1974, Stephen Hawking published a calculation that troubled even him. He had been working at the intersection of general relativity, Einstein's theory of gravity and spacetime, and quantum mechanics, the theory describing the behavior of matter at the smallest scales. These two theories, despite their individual extraordinary successes, do not fit together easily. They were developed separately, they use different mathematical frameworks, and combining them produces predictions that are sometimes uncomfortable. One of those predictions was Hawking radiation. In quantum mechanics, what appears to be the empty vacuum of space is not truly empty. The vacuum seethes with what physicists call quantum fluctuations, random, probabilistic variations in the energy of space itself. One way to think about this: pairs of virtual particles, a particle and its corresponding antiparticle, spontaneously appear out of the vacuum, exist briefly, and then recombine and annihilate. The energy for their brief existence is borrowed from the vacuum and returned. In normal space, this process has no net effect. But at the event horizon of a black hole, something different can happen. A virtual pair appears at the horizon. In normal space, the pair would quickly recombine. But at the horizon, the gravitational tidal forces are so extreme, space-time curving so sharply, that the pair can be separated before it can annihilate. One particle falls into the black hole, past the event horizon, beyond the point of no return. The other particle escapes into the surrounding space. The particle that escapes is real, carries real energy. It must get that energy from somewhere, and where it gets it from is the black hole. The black hole provides the energy for the escaping particle, and in doing so, loses mass. Over time, through the continuous emission of these particles, the black hole radiates away its energy and slowly shrinks. This is Hawking radiation. The name honors its discoverer, but it belongs to the universe. Hawking himself was initially disturbed by the result. It implied that black holes were not permanent, that something could effectively leave a black hole, in violation of what had seemed like an ironclad principle. He checked his calculation many times. Other physicists checked it too. The result held. And over the 50 years since its publication, Hawking radiation has become one of the most theoretically robust predictions in physics. Despite the fact that it has never been directly observed, the effect is too small for current instruments to detect. The temperature of Hawking radiation from a black hole is inversely proportional to its mass. Larger black holes emit colder radiation. A stellar mass black hole, say, 10 times the mass of the Sun, emits Hawking radiation at a temperature of approximately 60 nanokelvin, 60 billionths of a degree above absolute zero. Extraordinarily cold. In today's universe, where the cosmic microwave background is 2.7 Kelvin, a stellar mass black hole is actually absorbing more radiation from the CMB than it emits as Hawking radiation. It is gaining mass. But in the black hole era, with the CMB temperature dropped to essentially zero, the situation reverses. The Hawking radiation from even a stellar mass black hole will exceed the ambient background. The black hole will begin to lose mass. Very slowly. The time for a stellar mass black hole to evaporate completely, starting from a mass of 10 solar masses, losing mass through Hawking radiation until there is nothing left, is approximately 2 times 10 to the 67th power years. 2 times 10 to the 67th years. That is the evaporation time for a relatively small black hole. A supermassive black hole with 1 billion solar masses, roughly the mass of moderately large galaxy center black holes, will take approximately 2 times 10 to the 83rd power years. The largest black holes in the universe, those with masses of tens of billions of solar masses, will take up to 10 to the 92nd or 10 to the 95th years to evaporate. And the very largest, should any exist at the 100 billion solar mass scale, approach the 10 to the 100th power year timescale. A googol years. The evaporation of the last black hole takes a googol years. A number so large that writing it as a decimal would require 100 zeros after the 1. During its evaporation, something else happens too. As a black hole loses mass, it gets smaller. As it gets smaller, its temperature rises. The inverse relationship between mass and temperature means that a smaller black hole is hotter. The Hawking radiation becomes more energetic. The evaporation rate accelerates. At first, this acceleration is imperceptible, even over astronomical timescales. The evaporation rate of a supermassive black hole is so slow that the change in rate over billions of years is negligible. But as the black hole approaches the end of its evaporation, when its mass has dropped to something very small, approaching the Planck mass, the temperature rises sharply, the Hawking radiation intensifies, and the final evaporation happens quickly. In the final fraction of a second of a black hole's life, it radiates an amount of energy comparable to millions of nuclear bomb detonations. A brief, bright burst of gamma rays and particles, the last energetic event that particular black hole will ever produce. And then it is gone. The last black hole in the universe, the last remnant of the stellar era, the final object in the universe that contains a meaningful concentration of energy, will evaporate in a burst of Hawking radiation at approximately 10 to the 100th power years. 100 zeros. And after the burst, after the last particle and photon of Hawking radiation have been emitted and begun their journey across an essentially empty universe, after that last moment of any meaningful energy release anywhere in existence, silence. Not the relative silence of a dark era. Not the quiet of a universe between events. True silence. The silence of a universe where no process capable of producing or transporting usable energy is occurring anywhere. The universe will have arrived somewhere, and where it has arrived has a name. Heat death is not an event. It is important to hold that before anything else. The heat death of the universe is not a moment when something happens. It is not an explosion or a collapse or a flash. It is not a threshold crossed with a detectable signal or a dramatic before and after. Heat death is a condition that the universe approaches asymptotically over an almost infinite span of time. And it is the condition from which there is no return. To understand what heat death is, you need to understand what entropy is, not as a technical concept, but as an intuition. Entropy is a measure of how many possible configurations a system can be in. High entropy means many possible configurations, disorder, uniformity, sameness. Low entropy means few possible configurations, order, structure, concentration. The universe began in a state of extraordinarily low entropy. The Big Bang produced conditions of almost unimaginable order. An extremely hot, dense, uniform initial state from which everything expanded, clumped, structured itself. The Big Bang was not disorderly. It was the most ordered starting condition the universe could have had, and it has been becoming more disordered in the specific thermodynamic sense ever since. Stars are low-entropy objects. They are concentrated matter, burning fuel, producing ordered energy output. The process of fusion itself increases entropy. It converts hydrogen into helium, which has fewer possible configurations, releasing energy as heat and light that disperses into the cold surrounding space and increases entropy there. Every star that has ever burned has been a machine for increasing the universe's entropy. Every supernova, every cooling white dwarf, every evaporating black hole. The universe's entropy has been increasing since the first moment after the Big Bang, and it will continue to increase until it reaches a maximum. At maximum entropy, there are no more concentrations of energy, no hot regions and cold regions. The temperature everywhere is the same. There are no gradients, no differences in energy density from one place to another, and without gradients, no physical process can occur. This is the second law of thermodynamics. In a closed system, entropy does not decrease. The universe is a closed system. Its entropy cannot go down. And so the universe, moving inevitably toward higher entropy, is moving inevitably toward the condition where entropy is at its maximum and nothing can happen. That condition is heat death. After the last black hole evaporates, the universe will contain a diffuse background of particles, photons, neutrinos, electrons, positrons, all at a temperature indistinguishable from absolute zero. These particles will be spread across a universe so expanded that the average distance between any two particles is larger than the current observable universe. They will drift. They will occasionally interact if two particles ever come close enough. But the probability of any meaningful interaction will be extraordinarily low, and the energy available for any interaction will be extraordinarily small. No structures will form. The conditions do not permit it. The entropy is too high. The temperature difference is too small. Nothing can happen. And this state, this condition will persist. Not for a long time. Not for a very long time. Not for the longest time you can imagine. Forever. Not as a metaphor. Not as an approximation. But in the literal sense of the word, without end. Without limit. Without any subsequent condition that changes it. The universe in heat death will continue to exist. The particles will be there. The photons will be crossing the vast expanses of expanded space. The framework of space-time will persist. But nothing will happen within it that constitutes an event in any meaningful sense. No energy can flow. No work can be done. No information can be processed. No complexity can form. The condition is permanent. Some physicists, contemplating this, have noted a curious possibility: the Poincare recurrence theorem. In a finite, bounded system, any state will eventually recur. Given enough time, a system will return to any previous configuration, however ordered. If the universe is finite and if its quantum states are truly discrete, then given enough time, an almost incomprehensible duration far longer than a googol years, involving numbers so large they require notation systems that don't exist in common use, the universe might spontaneously fluctuate back into a low-entropy state. Randomly, without cause. A quantum fluctuation so improbable that its timescale makes the entire current age of the universe seem like a fraction of a fraction of a fraction of a second. This is speculative. It depends on assumptions about the universe's structure that we cannot currently verify. And even if it is possible, the timescales involved are so enormous that they are, for any practical or emotional purpose, meaningless. For everything that matters, for every duration that any mind has ever contemplated, for every span of time that any story has ever covered, the heat death of the universe is the end. The universe will be in the condition of heat death for longer than it was in any other state, for longer than the black hole era, for longer than any number, forever.